stringency. Hey, welcome back. So in my last video, I discussed about the engineering automation tool I built inside Excel, which is the ACI column interaction. If you haven't watched that, I recommend you do, and I will put it somewhere here. But the interesting part about that, after uncovering the problem with the simple goal of reducing the friction by removing the repetitive work, I realized the engineering logic that lives inside the Excel spreadsheet. It's not just a piece of engineering logic, it's a piece of capability, an automation capability, an engineering capability, or just simply capability. Now, the next goal is to extract that capability out of the spreadsheet. Again, you might ask, why do I want to extract the capability out of the spreadsheet? Why bother, especially if the spreadsheet is working and if it does the job well? Suppose we want to use the same capability from a different workflow, say a more automated kind of workflow. We can do that. Every time we need the capability, we have to go through the spreadsheet. Why? Because the capability is trapped inside of the spreadsheet. Now that's the problem we're trying to solve. So if we're able to extract that capability out of the spreadsheet, we can use it from anywhere and we can drive it from anywhere. All we need to do is to plug it into our workflow. That's what we're trying to do. So before writing any code, I want to show you this slide from the last video. I also showed you the exclusions, but this time I want to be explicit on exactly what are we trying to extract from the spreadsheet. And that is the core function that you see from the screen. The other components will just serve as a form of supporting or utility functions to run and build the whole interaction diagram. But the interaction diagram is not the capability itself. So this is not yet the whole column design application. We will exclude the reinforcement, how to choose the reinforcement specifically. That's not part of it. Also the checking of the column against given demands, not that. We will also not try to validate the detailing, which is the spacing checks you see on the screen. That's not part of the core function or the capability that we're trying to extract. And of course, naturally, we don't want any decision on how the project should be run. So in extracting the core capability, we will just try to answer the simple question of, given a reinforced concrete section, material properties, reinforcement layout, and a set of neutral axis position, what axial moment capacity does the section produce? So that is the core capability we're talking about. By the way, an important note on how I made this decision. I made this decision to put the boundary on what the exact capability is or what the capability should be. It's based on the fact that these ideas I've shown you earlier, they exist even before Excel. They exist outside of Excel. Therefore, they should continue to exist with or without the spreadsheet. All right, so now let's jump on the implementation. So again, this question is the only thing that the capability needs to answer. And I have here on the screen the overview of the input contracts and then the output we are expecting. Now, how do we now translate this into a piece of code to make it work? So I'm going to switch here on my main, it's a TypeScript file. By the way, I'm not going to go through line by line in detail, but I'm going to put this in a repo, which I would link somewhere below. But I'll walk you through how to implement each step. And I have here a set of numbers, 1 to 9, based on how we would attempt to answer these questions from the capability we're trying to extract. Starting with number 1, receive the inputs for one neutral axis state. So let's start with let's make it a function. Oh, the AI is good. Calculate neutral axis state. Now I want to call this calculate PM interaction, or simply PM interaction. No, it's all right. It's more explicit, the better. So this is our main function that would cover all these items from 1 to 9. And next is establishing the strain distribution. I'll put the number here. I'm trying to be verbose on the variable naming. It helps down the line when we need to put in the AI in with the code base. Note I put it under assumption because this value right here is taken directly from the ACI code, and later on we can change that if ever that changes. Although we know 0.003 is very much static throughout the history of ACI. But anyway, now this would inform us that we need to pass the assumption somewhere. So how I'm working here is I'm starting with the core engine, the core function, and we'll define the input contract as we go along the way instead of trying to imagine them exactly. So let's see how they emerge here. But the point is we will also define the input contract, but I deliberately skip that for the purpose of showing you how they would naturally come out of the function as they're required. Take note we are abstracting a lot of things here, but what I'm trying to show you is what is involved for us to arrive at the output. But don't think about the details yet on how to calculate these things. For example, the tensile strain would require an input about the reinforcement layout, which we would inject here as we already included it here. So later on, we would just say reinforcement layers or layout or however we want to call it. But let's just abstract those things for now. You know, when the strain distribution shows that we exceed the stress in the steel, so instead of using the actual steel stress, we just cap it to the Fy. I don't want to jump by giving this all to AI because it would just give us the output, but we would miss the opportunity to understand what's going on. The lesson I'm trying to show here is we're trying to implement the engineering model, the engineering knowledge, the assumptions, the calculations, which all of which form the capability. So it's important, but for now we could also use AI just for the auto-completion. Is that complete? Well, balance point. This is optional. Let's leave it for now because the original spreadsheet contains the calculation of the balance condition, but let's just skip it for now. Now, what we want to do is to fill in the inputs that we need for these to make sense, right? Maybe that's what's going on through your head right now. What are these? They're just empty. Well, I'm just showing you the individual functions that make up the whole capability, and they depend on each other in sequence until we arrive at this, and then our final output. Actually, well, we can say call the assemble point here. But anyway, that's just details. Let's go back, and I'm now going to explain the input part for this to make sense, and then after that we will go to the output layer. Geometry, yes, of course, the geometry. And to resolve the geometry, we need some helper functions. Now, this is responsible for how we would calculate the effective depth. I mean, this core function that we have, this calculate PM interaction, should just receive that. It doesn't need to be responsible for the calculation of the effective depth. And then we also need to calculate the compression steel. Technically, we can merge them into single function and then just put a boolean somewhere of which one we want to calculate, but for the sake of clarity, this is, I would say, better, and it's easier to test as well later on. Right, so they would return the effective depth and the compression steel depth, which we need. Actually, we don't need the whole geometry, do we? Should we put a flag somewhere, like output PM state? Should we say that? PM state nominal. Oh, the AI is really good. It's trying to predict what do we want, or what do we mean by the PM state. What I'm thinking is whether we want the output. I'm talking of the PM output state, output or output type. You know, I'm just thinking about this. Yeah, whether the factor, the ultimate, or nominal. And then the AI is suggesting about tension control. Oh, that's a good thing to add, but let's just note this. Nice to have. Type PM state, you know. Balance tension. Yeah, this is good. This is good. So I guess this is these are the main components. We can now calculate this the PM interaction based on these individual subcomponents. Again, I'm gonna speed run parts of this, you know, just in case. But again, I just want to repeat that I'm gonna put this code in a repo somewhere in GitHub, so I'm gonna link in the description below. Oh yeah, okay. So this is all right, because if we don't have a compression steel, which you know, we seldom see columns that don't have, you know, that only have reinforcements on one side. So this is just a safeguard that if in case the compression steel depth is not specified, just put it as 0. So that's why I put the optional, the question mark optional right there. This is the thing, right? This is the thing. I'm thinking if we should, you know, put an array here, since we're dealing with layers, so we don't know exactly how much layers will be there. But that's I would say that's good, but that's not a good approach at this point, because we're trying to overstep in terms of responsibility. The core function is not concerned of how the reinforcement will be calculated or where it would come from. The core function is just there to process it, to calculate it. So yeah, we could abstract the process. Now, when we go to the implementation of the reinforcement layers, there will be calculations right there that would produce the tensile steel with these two values only. whatever happens there, the processes that are involved in calculating that these two values, area and depth, regardless of how many layers, is no longer a concern of the core function. So, for example, if we have two layers here, we don't need to know that. We just need to know, if we have two layers, what's the total area and where is the the effective depth in the middle of those two layers or wherever. That is not the concern of the core function. So I just want to be clear with that. But that doesn't mean we wouldn't need to implement this. This should be implemented somewhere else, whether, how we want to use ultimately the capability. But for now, let's just focus on the capability. So this is a good separation at this stage. Tensile and compression, compressive, whatever. Because in the nature of a column, there are only two states for longitudinal bars, at least. So tensile and compression, tension and compression. So from here, we now have the tensile still. Just side note, sorry, my brain is jumping from different directions, but just a side note, I'm thinking we might not need the depth at the calculation part because we outsource that responsibility for these two. They are the ones responsible for calculating the depth, so they are the ones which need that information where the reinforcement is located within the section. But insofar as the PM calculation is concerned, we just need to know the effective depth, the total area. So yeah, we might not need the depths for the reinforcement. So if you notice, I'm leaning towards functional approach here because in this particular example, it is, as you can see, it is heavy on calculations and it's more on input, process, output. So perfect for functional approach. And what's important, I believe what is important is being able to validate each of these, functions. And, later on, perhaps I'd write a set of unit tests to verify them. So you'll notice that even if I define the parameters inside the PM interaction, I still pass them inside here because later on I'm planning to test these individually. That would be an easier way to do that, and also perhaps refactor this out of the PM interaction. Who knows? But that's the main idea. Well, I'm gonna stop this here. I'll just try to explain what we're doing, and I will implement the rest off screen. Again, I'm gonna put it in GitHub anyway, so you're free to check it later on. Essentially, we're following this to come up with a single interaction point given this set of parameters. Going back to this, what we want is to answer this specific question, and the capability exactly answers this. So we need to define this, which we did some of it, and then the final output. The final output is just capacity point, which are composed of PM and the neutral axis, the axial force, the moment at that. These three quantities, I would say, define the state at which the column is in for a given neutral axis. So that's good enough. Now, if you're thinking, how do we create the whole interaction diagram? And going back to the the architecture that I presented from the last video, that part would be inside the neutral axis loop. And that's the beauty of it. The point is, when we put this capability in there, this piece of capability doesn't need to know, who or what drives it. This is the main idea that I'm trying to present throughout this video, that I hope I was able to. So when we feed this inside that neutral axis loop, all we need to do is to feed in an array of neutral axes, and then it's gonna create the whole interaction diagram given the particular reinforcement, which I believe answers this now. Given a reinforced concrete section that I mentioned, geometrical dimensions, material properties, reinforcement layout, and the set of neutral axis positions. This particular word here, the set of neutral axis positions, it would just be an array of neutral axes. And the reinforcement layout would correspond to the old spreadsheets design space. So these two values are, we could say, dynamic. But the point is, the core capability, the core function, doesn't need to know anything about it. That's a beautiful thing that I'm trying to I'm lost. I'm trying to demonstrate in this video. So yeah, I'm gonna stop here and I'm gonna continue off screen. Let me know if you have questions. Sometimes my brain just jumps on different layers. Sometimes I tend to get stuck in the details, too much in the details. So it's a good exercise to always go back to the architecture and why are we doing this. So again, in summary, we're trying to answer these questions in order for us to define the core function, the capability which we're trying to extract from the spreadsheet. And this is the implementation of it. If you have any questions, again, please, I hope to see them in the comments and I would try to answer them. Also, the repo, I would upload this in a GitHub repo, which again, I would put in the description below. I hope you enjoy this and you pick up something, and I'll see you in the next one. Bye.